do last week? The main point is the Dennard scaling, just like the student asked, right? He's asking, are we still following the Moore's law? People try to read the paper I sent you. I put in the beginning of the class for this this lecture, right? By, I forgot his name, Giannani, right? So he discussed Dennard scaling is not Moore's law. Moore's law, if you really want to trace the original paper, he's talking about functionality. It's not by purely scaling. One is increased functionality through scaling. Another is through more smarter architecture. And that is what we are doing now. Dennard scaling is simpler, or it's just telling you how to scale the transistor. And this basically stopped now. But it is still very important for us because by understanding the scaling, you discover many important physics, right? Like what we discussed last time. So first of all, you say that how do you scale a transistor? You make the linear dimension and voltage and reduce them by kappa. And remember, I emphasize linear dimension include this depletion width. You also want to reduce the depletion width by kappa, okay? By doing so, then what will you get? You will have by doing so, then it means you also need to increase the substrate dopant by kappa because the depletion width, maybe you forgot, you don't have to memorize, but I hope that at least now I keep writing, you remember it's a square root, right? It's related to the doping concentration, related to the epsilon, and more importantly, is related to the voltage you apply to it, right? So if the voltage is larger, I have larger depletion width, right? So if I reduce my, if I reduce the V, right, because this is the requirement of this scaling, then I need to also increase the doping by kappa, then the overall W will be reduced by kappa. Then I achieve the nonlinear scaling, right? So I keep using this one as example because if you understand this example, I think you pretty much understand what Dennard scaling is about. And after all, why do we want to do this? Because we want to have a constant field, E equal to V divided by distance. I reduce the linear dimension and reduce the voltage proportionally, then I have the same electric field. Okay, why electric field is important? Because it's related to the reliability. When electric field is large, it generates a lot of hot carrier. You can damage the gate oxide. So we want to keep them the same. We cannot just reduce the dimension without reducing the voltage. Any questions, comment? And then we derive the equation for these three, right? The current, power, and eventually you find that the gate delay is reduced by kappa. But this is only true if your gate delay is dominated by the gate capacitance.
So just a quick question, I guess. When this translates over to actual like chip manufacturing, like my understanding is that we've been at about the same voltage for several years while we've been reducing size.
Yes.
Is that because the voltage is low enough to where we are allowed to go that small, or is there some other strategy?
No, you are right. It is not. So if you look at the scaling of the voltage, it is something like this, like what you said. It is a step size, right? Just because of the system, we cannot keep changing, right? It might go from 5 volt, 3.3 volt, and then to 1 volt. So the not scaling is just an ideal case, but we try to follow it. But in reality, we don't. So that's a good question. So in some cases, you might actually have the electric field becomes too high, and then the reliability becomes worse. But you use other method to elevate this problem. Yeah. So remember, this is just an ideal case, not what we're really doing in every generation. But overall, you will see that it is going down. So this one has a more instructional value, actually, right? But studying this, you understand all the problem of scaling. Do I answer your question?
Yes, it does.
Okay, good, right? So now let's go to gate delay. Maybe at this stage, you will start having something very vague. What are you talking about gate delay? Let's just think about an inverter. The inverter is going to drive, right? You have a signal, V in, right? You are going to change the V out to V in. For example, right, when this one goes up, then your output will go down. Right? Basically, you are going to discharge this node, right? But where is this node connected to? Usually it is connected to another gate. We can say maybe it's also an inverter. Doesn't matter. The point is it is proportional to the gate capacitance, right? So this is the voltage go in, this is V out. So what are we discharging? We are discharging the equivalent capacitance, CG, right? So that's why when we derive this equation, we use CG, which is C ox times WL as the loading capacitor. Is that clear to you? Right? So you remember when you're scaling, yeah, I make my transistor smaller and weaker. See that? Current is reduced by copper. But at the same time, I make the loading smaller also. And that's why my gate delay decreased by copper, right? But I keep emphasizing that nowadays, it is not dominated by COS. It also have parasitic capacitance, right? This is not just gate capacitance. If you really, for example, if you take EE224, right, which we will offer next spring, we will analyze all the capacitance. And you see that you also have CGD, CGS, and other capacitance, or even the wire capacitance. Right? You even have the wire capacitance, whatever, everything, C parasitic. So this is what you are actually discharging. Okay. So let's go to the new slides, right? So what are we scaling? Down to 65 nanometer. Okay. Gate capacitance dominate because the size is large. That's why you see we keep scaling the gate length to 65. But now new parasitic capacitance dominate, right? So we still scale it because we want to increase the density, but we scale slower to reduce the leakage. Remember the free leakage I mentioned last time? Can some of you tell me what are the free leakages that we have when we scale the transistor? Do you remember? Well, you need to remember to pass this class. So anyone, just give me one will be good.
It's a gate leakage.
Gate leakage. Yeah.
Tunneling.
Scaling. Right? When you scale, you have gate leakage. Very good. Due to tunneling. What else?
Junction leakage.
Junction leakage. What else?
Offset leakage.
Say again.
Subthreshold leakage.
Subthreshold leakage. Very good. Subthreshold leakage, right? Since you answered, can you explain a little bit? What is subthreshold leakage?
So when basically gate voltage is less than threshold voltage, so whatever the voltage happens in the transistor, that is known as subthreshold leakage. Because at that time, transistor should not be on.
Very good. Yes. So he is saying that, right? We have a transistor, right? And this is VG smaller than VTH. There's still leakage because the gate cannot control the substrate. So we have this subthreshold leakage. Okay. Now, if I make the gate length very short, then the control is even worse because drain and source are so close. So I have a lot of leakage. So that's why we don't want to go too fast, right? So it's slow down, okay? But overall, there's something we keep scaling. This one is something I want you to memorize. It's called contact poly pitch. Sometimes it's called contactor gate pitch, CPP, right? If you can say this in your interview, right? I hope that I'm right. Then I think it will impress people. I don't think many people know about CPP in the scaling, right? It's not about the gate. So let's take a look in this transistor. This is the source. This is the drain, right? And then this is the gate. Gate here is not really drawing the transistor. It's just showing you the location. The gate is here, and this is LG, right? Exactly the same as this one, LG, right? And then the contact, you need an opening. The contact cannot be zero width. This is a big deal because now the contact resistance is very high. You need to have a certain width. Otherwise, the resistance here is going to kill your transistor performance, right? Do not think that this is metal on heavily doped silicon. It is, but it has resistance because our transistor is so good now, right? So you have a width. And then between the contact and the gate, you have a spacer here, right? Here. And this is TSP. So what is the CPP? CPP is very simple. It's just that what is the minimum distance between the contact, right? And since it's periodic, you can see that it is just equal to LG plus TSP. But how many TSP? Actually 2 TSP plus WC. Can we check if I'm right? Yeah. Is that okay? Because this really tell you what's the transistor density. If you only scale the LG, but you are not able, if your technology require you to have a very, very large WC and TSP for a new LG, then it's useless. Okay, so they say, oh, I invented a new transistor. So good, so good, so good. This is very common. But then when you put into manufacturing process, your transistor need a larger TSP, need a larger contact, then it's not helping. Okay, so I hope that this is the takeaway. Even you don't understand what I'm talking about at this moment, CPP is a very important thing, right? So to be an expert, no more LG scaling is CPP. Okay, any questions? Now, if not, then let's take a look why CPP is so important. Here I show you a standard cell layout. I think many of you, in particular in our school, our students are very good in this standard cell system level, right? Many of them have an industrial experience. If you have, you probably know that when you make a chip, right? You don't lay out the transistor one by one. You actually do very long, and then you convert it to standard cell, right? And this standard cell then will place the layout in your final layout, and then you do routing. So here I show you something called FinFET, a 3D transistor. You're not familiar with that? Yes, that is okay. Just treat this as a source. This is a drain. This is a gate. That's it. And it's just a so-called 3D because the gate wrap around the channel, turn it on and off. It is easier to understand than planar if you think this as a water hose, right? Well, water hose isn't that you just squeeze the middle part to turn it off and relax it to turn it on. It's exactly the same. But because now you have the gate, you use 2 fingers to squeeze the water hose. So you have very good control, make it on and off. And that is nowadays technology. So each of this is like a fin, right? The fin on the fish. So that's why you draw this green one are the so-called fin. And this vertical one are actually the source drain contact. And you can have several fin. Here have 4 fin for the PMOS. So you have 4 transistor width, right? And then 4 fin for the NMOS, right? And what do I want to tell you? The size of the standard cell is going to determine your final chip density. And you can see clearly 2 matrices. One is what is the minimum metal pitch. This is on another layer. Why it is important? Because it's going to determine how I'm going to be able to connect this fin to the metal and do the interconnect. And another is from left to right, the contactor poly pitch. This is contact, correct? Yeah? No, this is not, sorry, I keep saying something wrong, right?
Hey,
This is
Professor,
the gate. Yeah.
and for the picture on the left,
Mm-hmm.
which part is source and drain? For the picture
Right.
on the left,
So first of all, I say something wrong. This vertical one is the gate. Okay. So source and drain will be this open area. We just did not show you the contact. But which one is source and which one is drain depends on your connection. So for example, this may be talking about two transistors in series. Then, for example, this will be source. This is the drain of this transistor, and then this is the source that connected together of drain this of the drain of this transistor, and then this is the drain. So it doesn't matter which one is. It really depends how you connect it, how you bias it. Because if you look at this 3D structure, the source and drain are equivalent. You cannot see the difference. The only difference is when you apply the gate bias. This is the same for the planar, right? Do I answer your question?
Okay, if we compare the picture on the left and the picture on the right,
Yeah.
the left is like 2-dimensional, the right is 3-dimensional. Then
Okay.
which angle you're looking in
Okay.
3-dimensional, you can get the 2-dimensional one. It's like if from the bottom to top or top to bottom or left to right.
Yeah. Okay. This one is I missed. This is the layout. So it's the bird view. You're looking from top. So if I call this A, B, you see the corner here, right? D.
Yeah.
I draw a square. Then it will be something like this is A, B, C, D.
Okay.
So this is looking from the layout from the top. Okay, so you see this gate. This is the gate running this line, right? And then this is source and drain here. And then each of this is the green line. This is the, maybe the best way for me to say that is to even color this as green, then you will see it very clearly. This is the green line you see from top. Now, do not match this directly one-to-one. For layout, you are not going to draw this diamond. This is something it grows from the fin in the process, but you don't need to draw it. After fabrication, you will get this diamond. But if you want to compare, this is the one. Okay, is that clear now?
Yeah.
Okay, great. Yeah. So I actually jumped. So this type of question is so important, right? I think many of you also got confused. Someone helped you to ask. So if you can ask, that would be very good. Yeah, sometimes. Yeah, please.
I have a question. The gates that are going across the fins, are those all, is it common to all the fins? So if you were to apply voltage to the gate, all the fins see that voltage?
Yes, in this layout, it is the case. So in this layout, they are all connected together, right? Let me still draw this one. Okay, this rectangle corresponds to this rectangle. It does. So they are connected. So by connecting them differently, you will get different standard cell. You might get LAN gate, inverter, NOR gate. Okay. So in our class, we are not going to teach this layout. So probably this is only one or maybe a few that you will see, but you can appreciate why it is important for density. But in reality, after fabrication, you get the one on the right. Okay. And now here, just to emphasize again, CPP is important. And that is how it has been scaling. Even up to 1, 2, 3, 4, 5, 6, 7 nanometer technology. It is still following this rule. This one actually is CPP times MMP, right? The goal is that you see we keep making it smaller and smaller, although the gate length is not. Is that okay? Right, feel free to stop me, right? because many of these things are not common. If you have not seen that before, you may get confused. And sometimes like this time, I failed to tell you the orientation. Okay. So why do we want to scale? Money, right? We do everything for money, really, the whole industry. So when we go to higher technology, better technology node, right, we actually increase the price because it's very difficult to fabricate the FinFET. A lot of more steps. So the cost, not price, the cost per unit area increases. The good thing is the area per transistor reduces, the density reduces. So the cost per transistor reduces, right? So it means for the same amount of function, we get more, it is cheaper, right? Of course, we need wafer volume. You need to think about that also. You cannot just make one wafer and then you say you are saving costs. No, you need to produce a lot. So if there's no demand in the market, this equation won't work, okay? Now let's step back a little bit. Go back to just planar. What is the best planar transistor? We need to learn a little bit, right? Although it is a little bit outdated, but not really, because nowadays all this SOI, they're still planar, right? The most profitable technology in the foundry is still the planar, 45 nanometer, 22 nanometer. FinFET not yet. They are fancy, but they are not the most profitable, right? So in planar, why I want to mention this, because this will be a frog leap for you if you did not study this before. You always learn a MOSFET, you have a gate, and we use polysilicon. No, nowadays we use metal gate. Why? Can someone tell me why I want to use metal instead of polysilicon? What's the difference between metal and silicon?
It's more conductive.
Very good. Because the resistivity rho, which is the resistivity, is smaller. Why do I care this? Maybe you cannot see it here. Let's go back to this picture. This is just RC delay when I propagate the signal from this gate to this gate. Even your gate is not conductive, I need to propagate AC signal, right? So the RC delay is going to determine your delay, right? Now a transistor so far, we cannot afford more delay. That's why we use metal gate. There's another reason, so-called poly-depletion. I won't go into detail because since they are not here now, so maybe it's okay, no poly-depletion. You will see this if you use power device. Basically, when you turn it on, you're going to form a depletion layer at the bottom. And because it's depleted, then you actually have a thicker gate or equivalent gate oxide, right? So this one, just know that you have this. Otherwise, not that important. I mean, it's important, but we don't see it much now. Dielectric, gate dielectric, right? We mentioned this already. We go from silicon dioxide to hafnium dioxide, or maybe other, but mostly hafnium dioxide. Why? I mentioned that already. Why we want to do that? What's the difference between hafnium dioxide and silicon dioxide? Different elements, right? But what is that? Yeah, please.
Yeah, it has high insulation capacity. Permittivity is high. Yeah,
Okay, both of you say the same thing, right?
it's a good insulator.
Higher permittivity, yeah. Correct? So that your capacitance equal to epsilon divided by T will increase, right? So at the same time, I can keep T, keep large T, right? I can keep large T. Why I want to make the thickness T? Why I want to keep it large? Why don't I make it very small? What will happen if it is very small?
Tunneling.
Say again?
Tunneling.
Thank you. Reduce tunneling. Okay. Everything has a reason, right? And then for the rest, I won't emphasize too much. First, right, we have so-called silici, again, just to reduce the resistivity. You let metal react with the silicon. Just know that you have silici. Silici is like default now, right? Halo extension, the extension, right? We, instead of, actually, this paper has some problem, actually. It is wrong. This one should be N plus, this should be N plus. So I think this book has some typo. You actually have a more nicely doped in this region. Why do we need that? We just to reduce Hawk carrier injection, right? We are not going to study, we will study a little bit in memory because we use Hawk carrier injection to do programming. But basically, this is to increase the reliability, right? Which called HCI. Right? I hope that maybe you just, if you love device physics, just try to understand, okay? Halo is just a doping to prevent punch through, to avoid the leakage. So halo is to reduce the subthreshold leakage. Right. I can tell you all this, we can go into detail, and that will be half semester of an advanced device class, right? But this is not the purpose here, okay? So, but I tell you all the critical thing, right? Let's do a better organization. First is the metal, reduce the resistivity. Second, we use high K to increase the capacitance, avoid leakage, right? Third, we add silici, again, to reduce resistivity. Fourth, extension to reduce hot carrier injection. And 5, halo to reduce subthreshold leakage, right? So you see, we make it smaller and smaller. All we are trying to do is to make the transistor better by reducing leakage and increasing the performance. Okay. Any questions? And I believe this one can be downloaded from internet. You just Google, you will get it. This is a pretty good book, right? But that is a typo. Any questions?
I have a question. So, is the very early MOSFET, were they using metal gates and then they switched to polysilicon?
Yeah, very good. So the very early MOSFET actually used something called aluminum. The problem of aluminum is that you cannot do so-called self-anneal because aluminum has low melting point. So you cannot activate the source string first. You cannot you cannot pattern the aluminum first and then do the source string because it's going to melt the aluminum. Later, they go to silicon and then do implantation because now implantation is available. Very early time, they cannot use implantation. They use diffusion. They add the dopant on top, a material with the dopant on top of it, heat it up so the dopant will diffuse into it. But then this is very difficult to use in the semiconductor process. Later, we use implantation. That's why you see this Dennard scaling is very interesting. For now, you don't understand why it's so important. But the paper is called Design of Ion Implanter MOSFET. So you can see that in 1974, ion implanter MOSFET is something new. Now no one will say I have an ion implanter MOSFET. Everyone knows that. Unless if you say a diffusion form MOSFET, then maybe that can be a paper, right? So you see that in 1974, people start doing ion implanter, and then they will try to think about how to scale it, right? Now, sorry, I go too far. So the point is, they start with aluminum, but aluminum is not good for scaling because aluminum cannot give self-aligned structure, right? I won't go into detail, right? And also aluminum, you cannot adjust the work function. Later, when they make the transistor small enough, the substrate doping increase, they realize that we actually need 2 types of gates. One is P-type, one is N-type, for so-called for PMOS and NMOS. They give you about the right threshold voltage, okay? So we keep going, and eventually we come to this problem. Actually, it's the opposite problem. We start going to SOI and also FinFET. And then we realize one thing is that gate depletion, right, resistivity. And other is that the threshold voltage is no longer good for FinFET because the threshold voltage, the work function for the N plus and P plus poly are very close to the conduction and valence band. If you do some calculation, it's not good for FinFET, right? Just trust me, right? And then they start using metal gate again. But now technology is so good, they can adjust the work function of the metal gate. And if you try to look into the paper by them, you see they actually multi-layer. Sometimes they use multi-layer of metal, very thin layer to adjust the effective work function. So this work function is soft. And also they have good conductivity. And another important thing is the so-called gate last process. Let me also mention here. Gate last means what? When they fabricated transistor, they still start with the poly because they can polysilicon, because they cannot put metal, just like aluminum, they will melt. After everything is done, they remove this poly gate and replace with the metal gate. They also actually deposit the hafnium dioxide in the same way, like this. All right, I don't cover this in this class, but I think it's important you should know if you say you know advanced device, right? Gate last process. It is like this. We start with silicon, okay? And then you remove it. And then you deposit with metal, right? Here you already form all the junction. So there's no problem, no thermal problem. Okay, because if I will start with the metal here, then when I form the junction, it's going to melt it. But this one, I don't have the problem. Is that okay? Any questions? Yeah, so it's, I mean, silicon semiconductor history is very interesting. Okay, so then we come to so-called equivalent scaling, right? So I just say that we can go to an ideal transistor is just like a hose, a water hose. And the gate is just like your finger. If you can hold the hole, squeeze the hose from all directions, you can control the hose very well. If you only push your finger on the hose against the floor or against the wall, the control is not as good, right? Pressing one direction, squeeze with two fingers, or just squeeze it by wrapping it around is very different. You know that, right? That is the same idea. So now, although the gate length does not scale as fast, but because we use this new transistor, metal electrode, high K dielectric, band structure engineering using stress, right? Low contact resistance. The result is the same as making the gate length smaller. Okay, so you see that there are 4 different things. String silicon, 2003 they did that already. High K metal gate. If you're not familiar with this, now you have to. This means high K, high dielectric constant. At the same time, you use metal gate. You know why, right? Less leakage, smaller resistance. Raise source string, make the source string higher so you have less contact resistance, multi-gate. Is that okay? Yeah, so there are too many things to learn. So you need to come to the class every time and then we may keep repeating and pay attention. Eventually you have the idea. And after that, that's not rocket science. You are as experienced as those who were in this industry for many years, right? And I get that some of you say, oh, you start with metal gates and then now come back. That's it, okay? Now, one problem that we are facing is so-called power wall. So what does it mean? You look at this graph, the power keep going up exponentially. And actually, this is very interesting. I went to grad school this year, and at that time, they were all talking about this power wall problem. And what they show us the picture is that they can use the Pentium processor to cook the egg. They show that. And then they say a few years later, I don't know which point, it will be the rocket nozzle temperature. Okay, and eventually it will be the surface of the sun temperature or the sun surface temperature. If you keep scaling in this way, no way we can do that, right? So see what happened. Intel at this inflection point, which is called inflection point in the paper, they slow down the frequency. Oh, so what is power consumption, right? It's the frequency times the CV square. C is the total capacitance of your chip, right? V is the voltage swing, and frequency is how fast you operate. If you don't operate, yeah, no power consumption. This is the frequency. If frequency has to slow down, we cannot keep going. Then what? Then that's a big deal. You cannot keep going. Then your transistor your CPU is not improving. But no, right? It keep improving since 2000, 20 years. Keep releasing new stuff, right? A lot of business arm, right? Acquired by different company. Why? Because they just reduce the frequency. At the same time, they add multi-core, use parallel processing. So this is an innovation in architecture. Okay. So you can see that the gate delay, yeah, it keep going down since 65 nanometer. But at the same time, we try to reduce the switching energy, right? So overall, the energy delay is smaller, right? So what do we care? Do not just think about the speed. Yeah, speed is important, right? If you cannot deliver what you want, it's a useless product. But at the same time, when you compare two technology, you want to compare the energy delay, because someone can claim that I have a very fast transistor, but it consumes a lot of energy. Is this a good CPU? Really depends. Maybe you really need this one, right? It's just like maybe in NBA in a team, someone may eat a lot, but he's so good, he always shoot 100% on target, right? And you do need him. You need to pay him a lot just because he needs a lot of energy to achieve the goal. But if not, if your goal is not to have 100% target rates, right, then maybe you don't need someone who eats so much, right? So energy delay product is important. So this is a key concept, energy delay. Don't just look at energy. You need to look at energy and also delay to compare technologies. Another is memory wall. What does it mean? You see that we have different type of memory, right? The CPU performance keep increasing, but the memory does not. And the worst things is what? Is the communication between your DRAM and your CPU. And that's why NVIDIA becomes so rich, because they produce GPU, right? One is that to do multiplication. Another is try to bring some memory very close to it, so that they reduce the speed and also reduce the energy consumption. And as a result, their GPU will be very suitable for the machine learning. Right? So this is something we need to break. You keep scaling your CPU, the LG. Yeah, it's very fast, but you cannot communicate to the data. What's the point, right? It's just like you are a very super smart scientist, but you never get data to analyze. No use. You cannot produce good paper, right? I mean, good results, right? So that's why people would say, we need to go to 3D architecture, right? So this is an example about the 3D architecture, the LAN. We are going to study it later. But basically, what it tries to do is the transistor actually is in the vertical direction. This is the gate. Word 9 is the gate, right? So I just pick one of them. This is the gate. And then this is source. This is drain. You see, I stack them just like the skyscraper. Many layers. Now they reach 100 layers already, right? Maybe you did not realize that. How come now the flash drive is so cheap? It's because of this 3D. They actually did not scale much laterally. They just stack up, right? I stack up 100 layer originally. It's 10 gigabytes. Now it become 1 terabyte. I sell you the similar price. Okay. So there are three in terms of scaling, right? We want to go low power. So here I want to spend a few minutes to go into something more serious. What I talked about earlier was hand waving, right? Now, how do we reduce the power? But let's look at the leakage power. Let me draw this graph again. We're going to draw it many, many times. This is the gate voltage. This is the log scale of the drain current, right? I already told you last time it's something like this. This is log scale. What does it mean? Maybe this is 1e minus 10. And this may be 1e minus 2. This is 1e minus 9. Do you see that? It's in log scale. Originally, you learn from the basic MOSFET in linear scale, right? Maybe I should draw here. It's like this. Right? This is linear scale, right? So this is 0. And then maybe this one reach 0.1, 0.2, 0.3. This is VG. So of course you say, there's no current after threshold voltage. That's not true. It just decreased exponentially. It decreased very fast. Okay, so this is something called subthreshold swing. I will define later. This log is called subthreshold swing, right? We will study later. But you can see, I think you already feel that, right? What is an ideal switch if you want you to make it good? You want to have something like this. And I suppose should not be able to draw this line. Because this is log scale, so you just go to negative infinity. I mean, to 0, so negative infinity in the log. This is an ideal switch. When I want to turn it off, give me 0 current. When I want to turn it on, give me very large current, right? But it's impossible. You can do this with so-called MEMS, mechanical switch, right? We won't cover here. But if you're interested, I can send you some paper. So people come up with something called tunnel effect. This tunnel effect is very interesting. It has a better slope. It has a better slope. So let's call it T-FET. And because it's a T-FET, you have better slope, so you have a lower power consumption. But generally, it also has lower ion, unfortunately. So it cannot replace all the transistor. It can be used for niche market, IoT, right? Very low power consumption. Another is NC FET, called negative capacitance FET. Right? That sounds very cool. How can you have negative capacitance? We will discuss it later. But it also have a similar characteristic. It also has low power, right? Lower power. Because it also have a more steep subthreshold slope. Right. But maybe let me don't draw it there because you cannot compare them. Otherwise, you think that NC FET and tunnel FET have this relative performance, but still it's very steep compared with regular transistor. Okay, so people are looking into this. Another is so-called CNT, carbon nanotube. Okay, so what is carbon nanotube? It's just a special carbon. They form the nanotube, right? They low power and also high speed, very low resistivity. We won't study in this class, but anyway, I hope you're aware that these are going on, right? And then for memory, how do we do that? We come up with some new memory, resistive memory, spin transfer top memory, phase change memory. We are going to cover in this class also. But what do they want to do? Finally, this is an idea proposed by Philip Wong in Stanford, right? He's a very famous. He was in IBM, then he became a professor in Stanford, and then now he's the CTO in TSMC when he's on his leave, right? So he's very famous guy. This is what they did in their school. They try to stack everything. First of all, you have some very fast transistor, carbon nanotube, very fast. 2D material, we are not going to cover. 2-dimensional material transistor, very fast. And then you stack them together. You can access the memory very fast. You have different type of memory for different purpose. You have spin top transfer memory. You have resistive memory on the top. They are very cheap, very dense, very high density. Basically, you put 1 terabit of memory on top of your computation unit. And then they have simulation and some experiment. Of course, they have not completely done, right? If they have completely done, they are very rich already, right? But some benchmark, they show that they can reduce the energy by 37 times, speed up by 23 times. But that is just what they can get now. Their vision is 1,000 times, okay, compared to what they have now. I mean, what people have now. So my message here about scaling is that first, you know that we've been scaling, right? In the Mark Bond interview I showed you earlier, and it starts with the Dennard scaling, very simple gate length scaling. I go into the math because it's related to the physics. You need to understand the physics, but that is that already. But Moore's law is not that in the sense of more functionality. How do we do it? In this case, we go to new transistor. We'll just show you the FinFET. We'll discuss. And then architecture, we try to put this new emergent device together, right? So besides the speed, we need to consider the energy and also the of the cost, right? The energy and the cost. Yeah. So 3D architecture, they will be used. So we'll repeat again later in this semester. Okay. So this is the picture. Any questions? Now, if no question, then let's go to device physics, right? Again, I don't expect you to use a lot of math, but we still need to, sometimes we use intuition, sometimes you use math. At the end, I don't require you to memorize too many equations, but at least you should know the equation for capacitance. You should know the depletion width is inversely proportional to the doping, right?